So, Chapter 15. So Exam 4 covers Chapter 15 and 16. 15 covers correlation, and you're going to use numerical measures to express the strength of the relationship between the two variables, develop an equation to express the relationship between the two variables, use the equation to estimate one variable on the basis of another. That kind of goes into Chapter 16, the equation and the estimate. So correlations measure the relationship between two variables. A direct relationship would be if as y increases, x also increases. An inverse relationship would be where x increases, y decreases, so opposite. And the most common one is Pearson correlation, which is represented by lowercase r. And for a Pearson correlation, you need to have variables that are measured either by interval or ratio level data. So the plot on the right, relationship between coffee sales and temperature, would that be a direct relationship or an inverse relationship? Yes. So the amount of beer sold and temperature would be a direct relationship. As temperature goes up, amount of beer sold also increases. So if you were to calculate the correlation here on the inverse relationship, you would get a negative correlation. This amount of beer sold and temperature would be a positive correlation. So the correlation coefficient measures the strength of the relationship between the two variables. It shows the direction and the strength of the linear relationship. And like I said earlier, it's both your variables have to be measured either interval or ratio levels scales. It only ranges from -1 to +1. If you get a correlation of -1 or +1, it means it's a straight line. 100% correlation between the two, or a perfect correlation. Values close to 0 mean there's no relationship between the variables. And negative values indicate an inverse relationship. Positive values indicate a direct relationship. So if it was 1, all your points would be on your line. So whether it's positive or negative doesn't affect the strength of the relationship. It's the magnitude of the correlation. So negative 0.5 is stronger than a positive 0.39. Has nothing to do with the sign. So here, the sales manager of Copier Sales of America wants to determine whether there is a relationship between the number of sales calls made in a month and the number of copiers sold that month. The manager selects a sample of 10 representatives and determines the number of sales calls each representative made last month and the number of copiers sold. So he wants to predict the number of copiers sold from the number of sales calls. So your sales calls are going to be your X or your independent variable, because that's the one that will change. And your copier sold is your dependent variable. It depends on the number of sales calls. So, like I said, the number of sales calls is X. The number of copiers sold is Y. And then you figure out the correlation by, that seems really strange. It's not supposed to be like that with the arrows. So the arrows here are indicating either superscript or subscript, depending on which way they're pointing. And so first you figure out your mean of X, which is 24. And your mean of Y is 44. Then you subtract your the mean of X from each one of your X scores, right? So 20 minus 24, 40 minus 24, 20 minus 24, 30 minus 24. You do the same thing for Y. You subtract the mean of Y from all of your points, your scores for Y. That gives you these two columns. And these are deviations, just like if you were calculating a standard deviation, it's the same things. They're deviation scores. Then you square both your deviation scores, these two, and then this is the sum of the cross products. So -4 times -14 equals 56. So you take your deviations for X, your deviations for Y, and multiply those, sum them, and that will give you your SP. Not what it's supposed to look like. You sum both your squared deviations, these two, and this would give you your sum of squares for X, 520. This will give you your sum of squares for Y, 893. And then if you wanted to calculate your correlation, your sum of the cross products, or SP, goes on top, and it's divided by the square root of the sum of squares for X times the sum of squares for Y. So that would be 620 over the square root of 520 times 893, and that gives, I think it's 0.9. Is that clear? Even though the picture is very unclear. Oh, 0.9. So that means that they are strongly related. There is a positive association, meaning as one increases, the other one increases as well. And they would be tightly clustered around a line that slopes up to the right. So if it was a negative correlation and it was 0.9, so it was just negative 0.9, that line would be sloping down to the right instead of up. So for hypothesis testing for correlation, you still do the same 4 steps of hypothesis testing. You state the hypotheses and select the alpha level, locate the critical region, compute the test statistic, and state your decision or conclusion. So the test statistic here would be R, and you would compare that to the table has the critical values for R, which I have one. And in order to reject the null hypothesis, you need to get a value for R that is greater in magnitude, not necessarily the sign, but greater in magnitude than the value that's on the table for the stated alpha level and degrees of freedom. For correlation, our degrees of freedom is n minus 2. So you've got two parameters you're estimating, x and y. So for a Pearson correlation of 0.5, for a sample of 20 participants for a two-tailed test, first you would state the hypothesis, select an alpha level. It's always going to be two-tailed. Locate the critical region. So under step 2, use the chi-squared chart. It's not the chi-squared chart, it's the correlation chart table. So if you'll need to know what happens if you selected 0.5 for alpha or 0.01 for an alpha level. Would your critical regions get smaller or get bigger with the different alpha levels? An easy way to figure that out is to look at the table. So if you look at the table and go to two tails at 0.05 and look at the very first number and compare that to two tails for 0.99 or alpha of 0.01, for 05, you would need to get, for 1 degree of freedom, a correlation of 0.9969. But for 0.01, you would need a correlation of 0.9999. So, and you can see as you go down the columns that the 01, alpha of 0.01, is always larger than the 05. So as you make alpha more stringent, or smaller, right, going from 05 to 01, your critical area, your critical region in the tails is going to get smaller. As you make it less stringent, your critical regions get bigger. So, for this particular scenario, how large of a Pearson correlation is necessary to be statistically significant for a two-tailed test of alpha of 0.05? Tells you there were 20 participants, so you go to degrees of freedom of 18 and over to 0.05, and you would need to get a correlation greater in magnitude than 0.4438. So you would need to get at least a 0.444 or 0.45 in order to reject. And that could be a negative 0.4. And then you compute the test statistic. As sample size gets larger, what happens to the size of the correlation necessary for significance? So as sample size gets larger, you can look at your table again. You just increase your degrees of freedom, right? That would be increasing your sample size. And if you look at DF of 40 compared to DF of 30 for 0.05, your critical value for the correlation to be significant gets smaller as you increase your sample size, meaning the critical region gets larger in the tails. So if your sample size gets smaller, you're going to need a stronger correlation in order to reject the null hypothesis. And then step 4, you state the conclusion, whether you would reject or not reject. For this, if we had a correlation of 0.5 and 20 participants, we would reject the null hypothesis. So suppose that a sample of 42 pairs of X and Y scores yields a Pearson correlation of 0.4. Does this sample provide sufficient evidence to conclude that a significant correlation exists in the population? If you were to test this at 0.05, two tails, you would conclude that yes, you have a significant correlation. So you would reject the null hypothesis because your critical value is a correlation of 0.3044. For your hypotheses for correlations, both your null and alternative hypothesis is always going to use the population parameter, which is rho. That's that italics looking capital P is rho. So you always have that in your hypotheses. And it will always be two-tailed, rho equals 0, or rho does not equal 0. Dependent versus independent variables. The dependent variable is the variable being predicted or estimated. The independent variable provides basis for estimation. It is the predictor variable. So, does the amount of health tech spend per month on training its sales force affect its monthly sales? What would be the dependent variable there? Yes. And that would mean training, or how much it spends on training per month would be your independent variable. Is the number of square feet in a home related to the cost to heat the home in January? So here, the number of square feet is your independent variable, and what is being predicted is the cost to heat the home in January. In a study of fuel efficiency, is there a relationship between miles per gallon and weight of a car? So the weight of the car would be the independent variable, and the miles per gallon would be your dependent variable. Does the number of hours that students studied for an exam influence the exam score? Exam score would be your dependent variable, and hours studied would be your independent variable. So R squared is the coefficient of determination, and it's the proportion of the total variation in the dependent variable, whatever is being predicted, that is explained or accounted for by the variation in the independent variable, x. And all you do is square your correlation. These values range from 0 to 1 or 0 to 100% of the variation in Y is accounted for by whatever x is. And it doesn't give you a direction of the relationship like a regular correlation does, because there's no negative ones. So for our copier sales example, the coefficient of determination, or R squared, is 0.576 or 57.6%. And that was found by squaring the correlation of 0.759. And then the interpretation of it is 57.6% of the variation in the number of copiers sold is explained by the variation in the number of sales calls. So chapter 16 gets into simple linear regression. And so the Pearson correlation measures the degree to which a set of data points form a straight line. or the relationship, the linear relationship between those two variables. Regression determines the equation for that line that best fits that data. So here, your dependent variable is the one being predicted or estimated, and it is predicted by your independent variables, which are also called predictor variables. So, is the number of square feet in a home related to the cost to heat the home in January? Same example as the last page, but now you're going to call your square feet your predictor variable, and the cost to heat the home your criterion instead of a dependent variable. You could call them either way. So for 2, your predictor variable is the number of hours studied. Your criterion is your exam score. So in regression, we use an independent variable x to estimate the dependent variable y. The relationship between the two variables is linear. Both variables must be interval or ratio scale. Same thing with correlation. It needs to be interval or ratio scaled. And the least squares criterion is used to determine the equation. So these, and the boxes are the definitions of these two. The least squares principle is a way of minimizing the sum of the squares of the vertical distance between the actual y values and the predicted y values. So, next page. Somewhere. All right. So, say you have number of copiers sold. And sales calls. And okay. Here is your line that goes that way. And these distances, so these are actual data points, some of which do fall on our best fitting line, some of which don't. The differences between, so the line is your predicted value of copier sold. The points are your actual values. For 2 calls, this person sold 2 copiers. So these are, the dots are actual data points. What this is referring to, minimizing the sum of the squares of the vertical distances between the actual y values and the predicted y values, it's squaring these distances between an actual point and the predicted line for all of your points. You sum those and you square that, and that is how they come up with the least squares line. It's a way to make sure that that line is in the middle of all your data points and not over here. So this line would fit these 3 data points better, but not all of them. And then you could have another line that fits these better, but not all of them. So don't worry too much about how it's calculated. Just know that it's trying to, the way that the line is calculated is in order to find one that fits all of the data points the best, minimizing these distances between your actual Y values and your predicted Y values. Your predicted Y values is your best fitting line. So here's our equation. Y hat is the estimated value of the Y variable for selected X value. A is the Y-intercept, meaning that when X equals 0, this is what Y will equal, or where it will cross the Y-axis. B is the slope of the line, or the average change in the predicted Y value for a 1-unit change, which could be either up or down in the independent variable. And X is your independent variable.
How is this different from like Y is equals MX plus B?
It's exactly the same. Every textbook uses different symbols, but exactly the same. And so this is basically what I drew over there. So in order to get the slope, which is B, and the Y-intercept, it minimizes those squared errors. So actually computing it, slope of the line is your correlation times the standard deviation of Y over the standard deviation of X. And to get your Y-intercept, you take the mean of Y and subtract the slope times the mean of X. And so for the same example earlier, everything messed up, you would divide your sum of squares for X and Y by the number of pairs of scores minus 1, or the number of X's minus 1, and then the number of Y's minus 1. And then take the square root, and that will give you your standard deviation. So, for our...
use Excel to do the test?
No. You're not supposed to use Excel. But it will also only be like 5 scores, not 25 scores. So you just plug in numbers, and we had the standard deviation of Y as 14.94 divided by the standard deviation of X, which is 11.4, and multiply that by your correlation of 0.9, and that gives you a slope of 1.31. And you always have to calculate your slope before your Y-intercept, because you need your slope to plug into the Y-intercept formula. So you just subtract the slope times the mean of X from the mean of Y, and that gives you a Y-intercept of 12.56. And then you can plug it into your generic formula for the regression equation. And 1.31 times X plus 12.56 is your regression line.
And that line is the line you're talking about?
The best fitting one. Exactly. So if you plugged in values for X here, the predicted values, Y, would be our best fitting line. They would be right on there, that line.
And your predicted line is your best fit.
Mm-hmm. So now we can do that. So if you plugged in a value of 1 for x, you would get a predicted value for y of 13.87. So the y-intercept, A, y equals 12.56 when x is 0. And that's it. So I think it's pretty straightforward. Anybody else have questions?
How does the null hypothesis relate to variables?